In this screencast, we're going to talk about some reactions of amines, sulfonylation, and elimination. So first, let's review the reactivity of the amino group. So amines can undergo acid-base reactions in which the lone pair on the nitrogen atom can abstract a hydrogen. So in this example, we have benzylamine reacting with hydrochloric acid. So the lone pair is abstracting a hydrogen. We're breaking this HCl bond, and then we're forming, in this case, an ammonium chloride. So the name of this is benzyl. So that's this group here, the benzene ring, the CH2, benzyl ammonium chloride. So these are called ammonium salts. So the nitrogen is positive, the halogen, the chloride is negative. So again, the nitrogen no longer has its lone electron pair. This molecule is a salt. So amines undergo acid-base reactions. And so the basicity of the amine, as we saw in the last screencast, varies according to the pKa value of the ammonium acid. So we can look at also the hybridization of the nitrogen to understand the basicity trend as well. sp3 hybridized nitrogens are greater bases than sp2, which are greater bases than sp. And so the reason that is the greater the S character, the weaker the base. And again, that's due to the shape of the orbital and the distance from the nucleus. So what this is basically saying that the hybrid orbital here, this sp orbital, because the s orbital is spherical, that contributes a greater portion to this sp, meaning the electron pair is closer to the nitrogen. It's less available to be bonded, as sort of seen what the requirement is in an acid-base reaction. You have to donate that lone pair. So in sp3, where there's the p3, the orbital is more dumbbell shaped, so it's further away from the nitrogen. It's more available to abstract a hydrogen. So here we have triethylamine is a greater base than pyridine, which is a greater base than acetonitrile. So nitriles really aren't terribly basic. It takes quite a strong acid to protonate the nitrogen. So in an acid-base reaction, the amine is protonated. When the amine acts as a nucleophile, it is alkylated. So here we have a primary amine. This is cyclohexylamine. We're reacting that with a primary bromide, benzyl bromide, and then the presence of this base here, potassium carbonate. And what this base does is neutralize the HBr that's formed. So essentially what happens is the lone pair on the nitrogen attacks the carbon bearing the leaving group. That's the SN2 reaction. And so in this case, we would end up with a secondary amine, and this would be the monoalkylation product. So now the issue with these sort of reactions is that you're forming now, when the reaction is in progress, you're forming a secondary amine. And so this can also be nucleophilic because this nitrogen has a lone pair. This can also react with the starting material. You can get dialkylation. So notice 1, 2, 3. Now we have a tertiary amine. And so this is also can act as a nucleophile. And this can react with the benzylamine to form the quaternary ammonium salt. We call it quaternary because we have 1, 2, 3, 4 carbons. Quaternary ammonium salt plus minus, that's the salt. So these reactions are typically difficult to control in terms of just isolating the monoalkylation. So to get around that, we use the strategy of reductive amination. So for example, if we want to make this particular secondary amine, we start with the same cyclohexylamine. We're going to condense it with benzaldehyde to form the imine that's shown here. So again, we have a primary amine and aldehyde. We're forming an imine. We can then reduce that imine with sodium cyanoborohydride. So essentially, we're reducing here, and then we're ending up with only this desired secondary amine. Another reaction that amines can undergo is called acylation. So notice the difference between alkylation and acylation. In an alkylation, the electrophile is at an oxidation state of 1. So again, this carbon is bonded to one heteroatom. We're just counting that single bond. That's oxidation state of 1. In acylation, the electrophile is at an oxidation state of 1, 2, 3. So what's going to happen, if we're starting with aniline here, we're going to end up with an amide. So we're at oxidation state 1, 2, 3. We're doing a nucleophilic acyl substitution. So we're forming that bond there, the amide bond, and this molecule is called acetanilide. Pyridine, which is a base, is there to neutralize the acetic acid that is formed after the reaction takes place. So another example using a different electrophile, in this case an acid chloride. So again, 1, 2, 3, acid chloride. Triethylamine is our base that neutralizes the HCl that's formed, and dichloromethane is the solvent. So if we take ethylamine, we end up with N-ethylbutanamide. And so this is a secondary amide. So we're counting 1, 2, that's where the secondary comes from, secondary amide. Another reaction that's similar to acylation is called sulfonylation. And instead of having a carbonyl, we're ending up with a sulfonyl group, and we produce a sulfonamide. So if we have cyclopentylamine, again, this is a primary amine, we're going to react with this molecule here, which is called benzene sulfonyl. There's the sulfonyl group, chloride here. So that's the leaving group. We're running this, and dichloromethane is the solvent. Pyridine is the base, which neutralizes HCl that's formed. So this forms a sulfonamide. So it's like an amide, except instead of a carbonyl, you have S double bond O, S double bond O. So this is a sulfonamide. So sulfonamides are more acidic. Sulfonamide NH bonds are more acidic than their amide or amine counterparts. So if you look here, this NH bond has a pK of about 16, so that's about similar to an alcohol. And the reason that is because now you have a strongly electron withdrawing group bonded to the nitrogen. So recall an amide NH bond is pK is about 25, and a regular amine NH bond is about 40. So you can see that by acylating the amine, so through an acylation process, you drop the pKa quite a bit. Through a sulfonylation process, you drop it essentially by half. So another reaction of amines is oxidation. So here's pyridine. Again, this is, imagine benzene and substituting one of the CH groups for a nitrogen. The lone pair on the nitrogen is nucleophilic. If we react that with an oxidant, hydrogen peroxide, we will form an NO bond. So this is called pyridine N oxide. So these are pretty common oxidation products that can even happen in the presence of air. So other conditions, if we have a tertiary amine, so triethylamine, MCPBA, you'll recall, is metachloroperoxybenzoic acid. This can form an amine N oxide. So lastly, this final reaction is called the Hoffman elimination. And so the NH2 group, like the OH group in an alcohol, is a pretty bad leaving group. The Hoffman reaction, you can actually make it into a leaving group. And typically the conditions you use are methyl iodide. And what's going to happen is the amine will undergo peralkylation. So we saw that was an issue with amines is polyalkylation. So if we take a primary amine and we treat it with an excess of methyl iodide, notice we have lone pair, 2 hydrogens. So we're substituting all of those now for methyl. It's 1, 2, 3. So that's per alkylation. Now we're ending up with a quaternary ammonium salt. So we have this ammonium iodide. So we can then take this material, treat it in the presence of a base, silver oxide under aqueous conditions, water and heat. And essentially what's going to happen now is this triethylamine group is going to be the leaving group. So the alpha bond is the bond to the leaving group. We have beta, beta. These are 2 different beta. That's what the beta prime means. This beta group has 3 hydrogens. 1 of them is shown. This beta group has 2. 1 is shown. And so under these conditions, the major product is going to be the elimination from the the least substituted carbon. Stated another way, the carbon bearing the most hydrogens. And so when this is an E2 reaction, so when that happens, you get the double bond here. So the major product would be 1 hexene. And so that's the least substituted alkene. Again, that's due to sterics. So if we eliminate from beta prime, again, that's the most substituted carbon. When that happens, we get the 2 hexene, and that can be either trans or cis. These would be formed in trace amounts, if at all. So this was a screencast on the reactions of amines, focusing on either the basicity, where the nitrogen lone pair acts to abstract a hydrogen, or where the nitrogen's acting as a nucleophile to undergo alkylation, acylation, sulfonylation, oxidation, or we can do an elimination through the Hoffman reaction.